Hello, today we're going to be talking about the life cycle of a star, but before we can get into that, I've got a video to show you.
Hi,
Hi,
you're on
you're
a
on a
rock,
rock,
floating in
floating in
space.
space.
Pretty cool, huh?
Some
Some
of
of
it's
it's water.
water.
Actually, most of it's
water.
water. I
I
can't
can't
even
even
get from here to there without buying a boat.
It's
It's sad.
sad.
I'm
I'm
sad.
sad.
I
I
miss
miss
you.
you.
How does this happen?
A long
A long
time ago, actually never. And also now, nothing is nowhere. When? Never.
Never.
Makes sense, right? Like I
Like I
said,
said,
it didn't happen. Nothing was never anywhere. That's why
That's why
it's been everywhere. It's been so
so
everywhere, you don't need a
a
where. You don't even need a when. That's how every it gets. Forget this. I want to be something. Go somewhere. Do something. I want things to change. I want to invent time and space. And I know it's possible because everything is here and it probably already happened. I just don't know when to start.
And that's exactly where it started.
Oh, I
I
paused it.
I think there's a universe now.
What's it made of?
Quarks and stuff.
That's a thing.
In a place.
Don't
Don't like it?
Try a new place.
At a different time.
Try to
stick together because the world is going to get bigger and emptier.
But it's
But it's not empty yet. It's still very full and about a jillion degrees.
Great
Great news, the quarks are now happily married in groups of three called a proton or a neutron.
And there's
There's
something else flying around too that wants to join in but can't because it's still too...
Great news, the protons and neutrons are now happily married to each other. Some of them even doubled up.
Great
Great news, the electrons have now joined in. Congratulations, the world is now a bunch of gas in space.
But it's
But it's getting closer together.
And it's
And it's getting closer together.
And it's
And it's
getting
getting
closer together.
New ships got made.
Some
Some stars burn out and die. Bigger stars burn out and die with passion. It makes them brand new, way crazy. Which allows newer, more interesting stars to be made and then die and explode into
So now stars have cool stuff around, like rocks, ice, and funny clouds, which can make some very interesting things. Like this ball of flaming rocks, for example. We just got hit with another ball of flaming rocks, and it kind of made a mess, which is just...
So that's kind of a little bit what we've talked about leading up to this and what we're going to be talking about today. If you didn't submit your Big Bang timeline or just need a refresher, about 13.8 billion years ago, some people say 13.7, either one of those is okay. The Big Bang happened when the universe formed. It took not very much time, a couple seconds, a couple minutes before we had nuclei, just protons and neutrons, but it was still too hot for electrons to join in. It took 380,000 years before we got to what's called the recombination era. And that is when electrons were able to join in and we got our first neutral atoms. Then it took a couple 100 million years. It's hard to pinpoint exactly when, but between 1 and 500 million years before we got the first stars and then galaxies. And another couple billion years, it was 4.6 billion years ago that our solar system formed. And we're going to talk more about that later. But all of that stuff in between about stars are born and die and other stars burn out and die with passion, that's what we're going to be getting into today. So, the Big Bang made hydrogen, helium, and a little bit of lithium. And those are, the most abundant elements that we've talked about before. But where did everything else come from? We've got 100 and something elements on our periodic table. Where did all of the other elements besides those three come from? They come from stars. So, in a ball of gas far, far away, the forces of gravity and pressure are engaged in an eternal struggle. This delicate balance, along with temperatures of millions of degrees, allows for nuclear fusion of elements in stars' core to fuse. And we get episode 1, the birth and youth of a star. So, stars start in a nebula. A nebula is a beautiful cloud of gas and dust. These are what you see. All of the prettiest pictures of space are these colorful, bright clouds of gas and dust. And this is where all stars are born. So everything starts in the nebula. If you're using the chart that I gave you, this is going to be the very first box in the bottom right. We've got this beautiful giant cloud of gas and dust where stars are born. It is mostly made of hydrogen and helium, the two most abundant elements. As we'll see later, there can be other stuff in there too. So we get all of these pretty images. This is the Lagoon Nebula. This one is called the Horsehead Nebula. If you look right here in the center, it looks kind of like a chess piece. You can see the kind of horse head. I'll tell you right now, astronomers are either really good or really bad at naming things, and there is no in between. So names are either going to be spot on or make no sense at all. This is called the Carina Nebula. It's one of the prettiest ones, in my opinion. So remember, this is mostly gas and dust, mostly made of hydrogen and helium, but there will be other things in it. This is the Eagle Nebula. It is one of the most famous nebula out there and has some beautiful dust sculptures. Like this one you can zoom in on. To give you an idea of this, that tower is about 10 light years tall. The closest star to our sun is 4 light years away, so more than double that distance. This tower is 10 light years tall. If I zoom in at the top, there's this structure up there that I think looks kind of like a blob dabbing. But a nebula get funny names mostly like when you look up in the clouds and see what shapes you can see. It's what do you see when you look in the nebula? If I zoom back out so we can zoom in on a different part, this structure is called the Pillars of Creation. It is probably one of the most famous structures in a nebula. There are lots of really gorgeous pictures of this in different wavelengths. Remember, we can take pictures in different wavelengths to get a different view of what it looks like. So this is a very well photographed image. Here's a different view of the Eagle Nebula. So maybe now it's a little bit more clear to see. We've got a wing, and here's its beak, and kind of looking from above, going out into the other wing. This is a view of the Eagle Nebula. Here is the Fox Fir Nebula, where I can see kind of a fox head over here. Maybe it looks more like the profile of a cow, but these get their names just from what they look like. So within these nebula, we get things called proplyds. A proplyd is a shortened form of protoplanetary disk, and it is where parts of the nebula clump together. Now, to be clear, it is called a proplyd or a protoplanetary disk. That doesn't necessarily mean there are going to be planets there. A proplyd is where a star is going to start to form. Like I said, some names are really bad. A protoplanetary disk doesn't necessarily have to have planets. But those pieces of the nebula that are clumping together are going to continue to clump together through gravity and get more compact and more hot, and they will form protostars. So I want you to think about a prototype. A prototype is like an invention before the final version, right? It's the first attempt before you get the real thing. So a protostar is not a star. It is the first attempt. It could become a star, but it is not a star yet. So these are some proplyds and some protostars, but they are not yet stars. So if you look here, this is another view of the Carina Nebula. You can see all of these different places where we've got gas starting to clump together. Those are going to be your proplyds that will form protostars. When it starts to get really, really hot, upwards of 10 million degrees Celsius, this is when the exciting stuff happens. This is when we get nuclear fusion starting and a star is born. Call Lady Gaga because we have a star. So nuclear fusion is the key here. Remember, if you have learned this before or if this is brand new, nuclear fusion is when two atoms slam together two or more atoms slam together to make a heavier element. So in stars, most often it is two hydrogens smashing together to make a helium. And that gives off light and heat in the process. Nuclear fusion is the most important thing to remember when it comes to stars. It is what causes stars to shine bright and to burn intensely. So if you're using that chart I gave you, there is a box at the bottom of the chart that is for nuclear fusion, for you to know It is two or more atoms combining to make something bigger, and that is what defines a star. Fusion has to be going on in order for it to be considered a star. So here we've got what you could call a stellar nursery. All of these are baby stars. Fusion has just started, and we are beginning to get some stars out of this mountain of gas and dust. Here we've got kind of a cradle. We've got a baby star in the middle, which is actually surrounded by some older stars. Some protostars and some stars don't make it. They are not going to survive this eternal struggle. So in the box below the star diagram, if you are using that chart I gave you, there is something with arrows pointing in and out. That is because there is this struggle between two forces, and stars have to maintain a balance between the two forces. So on one hand, we have gravity pushing in. The mass of the star, everything wants to sink to the center. Gravity is pulling everything into the center and squeezing it smaller. On the other hand, nuclear fusion is like a little explosion going off, and there is pressure pushing out. So we've got gravity pushing in and pressure pushing out, and these have to be in constant balance for the star to maintain its life. And we're going to see later on in the life of a star what happens when the balance gets upset and one of these things wins out. So gravity pushes in and pressure pushes out. So we talked about nebula and then protostars in protoplanetary disks. And now we are finally moving into actual stars. And a key thing to know is that the life of a star is determined based on its size. So we're branching into two different paths here. We've got a fork in the road. The top path is going to be an average low mass star, and the bottom path is going to be a high mass star. So the smaller stars follow one path and the larger stars follow another. And this part is called the main sequence. And this is going to be where stars spend most of their life. So the main sequence is the big long rectangle after protostar, if you're using that sheet I gave you. This is the longest stage of a star's life, and that's why it's a long, thin box. And this is a picture of our sun. Our sun is currently in the main sequence, and it will be for another couple million years. So in the main sequence, stars spend most of their time fusing hydrogen into helium. All day, all night, nonstop, constantly taking two hydrogens and combining them into a helium. And they will keep doing that until they run out of fuel. And how long that is depends on their size. So I want you to take a second and think, which is going to run out of fuel faster, a big star or a small star? Another way to think about it is which kind of car uses more gas, a Hummer or a Prius? The Hummer, right? It's going to burn through its fuel a lot faster. So bigger stars have shorter lifespans. They spend less time in the main sequence. Big stars measure their life in millions of years. Small stars measure their life in billions of years. So small stars last for a lot longer. Our sun is 5 billion years old, but that's only about halfway through its life. We've got about through its main sequence time, we've got about another 5 billion years to go. But eventually, our sun and most stars are going to run out of hydrogen. So what happens when they run out of hydrogen? And that brings us to episode 2, the fate of our sun. So we have our nebula that leads into a protostar, which goes into the main sequence. Both high and low mass stars have a pretty similar next step, and that is going to be a red giant or a red supergiant. Our sun is lower mass, so it is going to become eventually a red giant. So here we've got the sun, we've got the earth, and eventually our sun is going to expand into a red giant. And we probably aren't going to make it. So this red giant, eventually in 5 million years, the sun will expand, it will get a lot bigger, and it will probably absorb Earth. So red giants, the star is going to shrink at first, but then when it shrinks, it is going to get a lot hotter. And with that heat, it will be able to fuse helium into carbon. And once that happens, it's going to grow 10 times bigger. It's going to start glowing red because when it expands, it will cool down a bit. So maybe you remember or you've learned or seen before that when you've got a flame in front of you, red is actually a cooler flame and blue tends to be a hotter flame. So these red stars are a little bit cooler, but it's a lot bigger. So here is an actual red giant. This is called R. Sculptoris. The kind of spikes and circles you see around it are an effect from the telescope and from the camera, not something that you would otherwise see. But these are much bigger and red stars. So to give you another size comparison, we've got some planets. We've got Pluto, Mercury, Mars, Venus, and Earth. And now we'll jump up a bit and we'll compare to the gas giants and jump up a little bit more. And Pluto is maybe a pixel and Earth is a little bit bigger, still barely visible. And there's the sun as it currently is in the main sequence. Now, Sirius is the brightest star in the sky. Pollux is one of the twins in Gemini. Arcturus is in the constellation Boötes. Pollux and Arcturus are considered red giants, so you can compare them to the size of the sun right now, much bigger. If we keep getting bigger, we can see some Rigel and Aldebaran down at the bottom. But if we keep going, there is Betelgeuse is how you pronounce that. It's not Betelgeuse or something. It is Betelgeuse. And Antares. Those two are red supergiants. So red supergiants are what happened to high mass stars. It's the exact same as a red giant. You just started with a bigger star. So a large or high mass main sequence star will eventually become a red supergiant. And it's the exact same process. They shrink and then get really big and start fusing heavier elements. They are the biggest stars in the universe, and they can fuse elements all the way up to iron. So we got hydrogen and helium and lithium in the Big Bang, and then we could fuse up to carbon in red giants, and now we're fusing all the way up to iron in red supergiants. So Betelgeuse is a red supergiant that is in Orion. And we're going to compare it to the orbit of Earth or Jupiter. This star goes as far out as Jupiter does from our current sun. That is just the size of this star. It is huge and it is massive. And like I said before, when we're looking at stars, it's almost like looking into the past based on how far away they are. So Betelgeuse is between 500 and 700 light years away. So when we look at Betelgeuse, we're actually seeing what it looked like 500 years ago. So Betelgeuse is here within Orion, the constellation, and it is this massive red star. So we talked about nebula, protostars, the main sequence, red giants, and red supergiants. We're going to keep going with what could happen to our sun and what happens to low mass stars. And it's going to be, this is a bad name, a planetary nebula. I can't tell you why they called it planetary nebula. There's not a good explanation. It doesn't necessarily have anything to do with planets, but this is what happens to a low mass star after it becomes a red giant. So in the battle between gravity and pressure wins. The core shrinks and the outer layers of gas get kind of spit out, puffed away. So pressure just pushes all of the gas away. And you get some really beautiful nebula. Here we have the glowing eye, the ring nebula, and again, all of these are real pictures. The cat's eye, or sometimes called the rose nebula, those are both the same, just taken using different telescopes. We've got the Eskimo Nebula and the Hourglass Nebula. This one's called the Butterfly Nebula. So all of these are planetary nebula, and the gas just gets spit out. Pressure wins, and it pushes all of that gas away. The last step for a low mass star is going to be something called a white dwarf. It is the remnant, the leftover core after a planetary nebula. So we have this red giant. The core collapses into this tiny little ball. The gas on the outside, pressure wins, and it spits all of the gas out. So a white dwarf is this tiny leftover core, and on average, it is the size of Earth. That means it's got incredible density. So let me back up. Here's the sun. The sun is going to become a red giant like Arcturus, and that is going to get squished down to the size of Earth. Something as big as Arcturus, all of that mass is going to get squished down to the size of Earth. So it's going to be very, very dense. And one really important thing here, nuclear fusion is no longer occurring. That's important. This is not fusing new elements anymore. It has stopped fusing. So eventually, a white dwarf will burn out. It will fade away, and we won't be able to see it anymore. And when you look at all of these planetary nebula, the exact same ones we were looking at before, you can see the white dwarf at the center of it, right there in the middle. The white dwarf is always just right in the center. The left behind core where all of the gas got spit out. You can look up into the sky and see a white dwarf. They are hard to see because they aren't as bright. But Sirius, the brightest star in the sky, is actually 2 stars. It is a binary system. And one of those stars, Sirius B, is a white dwarf. So if you were able to kind of block out the light of Sirius A, the bigger star, you would see Sirius B, this little white dwarf. And these are small, mostly dead stars. So if you've got a big wish, save it for a big star. That takes us to episode 3, the death of a big star. So we already talked about the red supergiant, which was the same as a red giant, just bigger, super. So what comes after that? We've got this red supergiant where something's got to give, and there's an explosion, and we get a supernova. So again, these are going to be some of the prettiest pictures. But a planetary nebula, pressure 1, in a supernova, gravity wins. Nuclear fusion stops because the star has run out of fuel, and so gravity pushes everything in. There's no pressure to push out anymore. And the collapsed star explodes. And you get these huge explosions that are just beautiful images. So here is Eta Carinae, which is a supernova. This is not a supernova. This is a picture of a galaxy. But this is a picture of the exact same galaxy when a supernova is occurring down here at the bottom. So that star is not even really super visible, but when that supernova happens, it is the brightest thing in the sky. And it is this massive explosion that makes everything else look dimmer by comparison. So in a supernova, we had hydrogen, helium, and a bit of lithium formed in the Big Bang. And we have some elements formed through fusion. Pretty much every other element we got from a supernova. These are explosions where elements are just flying around, going wild. A lot of crazy stuff happens in a supernova. So there are some elements that were made in a lab, but after iron, pretty much every element came from a supernova. Anything heavier than iron came from an explosion. So there is all of our elements, all of the elements that make up you and me and my computer and my desk and my pet dog, and everything came from either the Big Bang, a star, or a supernova. So all of this stuff formed in space first. And supernova make these, again, beautiful pictures. This is a really famous supernova remnant. This is called the Crab Nebula, and it was one of the most widely observed supernova in the year 1054 AD. Chinese astronomers in particular kept incredible notes. They called it, I think it was the second sun, and it like lit up the sky for a while because it was this bright supernova, this huge explosion. This one's just called Supernova Remnant 1987A, but you can see where it looks like there was an explosion and stuff is getting pushed away. So we've got our nebula and protostars that made the main sequence, and red giants, which then became planetary nebula with a white dwarf at the middle. On the other side, we've got our high mass stars that became red supergiants that explode into supernova. But an important thing to note is that the stardust, the gas, and the dust left over from these explosions from supernova and planetary nebula doesn't have to just sit there forever. It makes a nebula. Remember, a nebula is just a cloud of gas and dust. So those element-rich leftovers of an exploded star or a planetary nebula can be recycled and reused to make new stars. And kind of like it said in the video, now there's going to be crazier stuff in that cloud of gas. And so you can end up with what we call a protoplanetary disk that could have planets forming now. So we have stars forming from all of this gas and dust. And with all of the other crazy elements, you can make planets. And we're going to get more into how did our solar system form later on. But so it's important to know that recycled stardust can lead to new stars and planets around those stars. We are almost done. What comes after a supernova? We got two choices. The first one is going to be a neutron star, or sometimes a pulsar. This is kind of the same idea as a white dwarf. You're going to have some teeny tiny little remnant, except this is going to be the mass of that red supergiant, the size of Manhattan. So all of that mass compressed into an incredibly small, dense ball. One spoonful of this would hypothetically weigh as much as Mount Everest. It is that dense. This is an artist rendition of a neutron star. Again, like a white dwarf, there is no fusion happening here. So it will die out. Some neutron stars spin and shoot out jets of energy and look like they are pulsing. So we call those pulsars. And they spin around, and every once in a while we get to pass this jet of light and energy. This is one called the Vela pulsar. Here's one that is sometimes nicknamed the Hand of God, or pulsar B150958. This is the pulsar that is at the center of the Crab Nebula, just viewed in X-ray. And lastly, maybe the thing you've been waiting for, from supernova, you can also get black holes. Black holes only form from the most massive stars. Only the biggest stars will explode into a supernova and then make a black hole. And gravity is so powerful that nothing can escape. So this is kind of an artist rendition of what a black hole looks like. But maybe you remember last year, the first actual picture of a black hole was taken. This is a real picture of a real black hole that we took for the first time last year. And this is an idea of what it could look like, otherwise an artist rendition. Light doesn't escape, and light can get bent around the black hole, but nothing can escape. There's also this idea called lensing, where again, light is being bent around the black hole. So if a black hole were to pass in between us and our view of some other galaxy, it would look like everything is getting bent around the black hole. So there is our full cycle from start to finish. We start in a nebula that becomes a protoplanetary disk with protostars. Low mass stars will be in the main sequence, become red giants. Eventually, pressure will win, and you'll get a planetary nebula that can recycle stardust and will also make a white dwarf. On the other side, you have high mass stars, which have shorter lifespans, like a Hummer going through gas more quickly, that will become a red supergiant. Gravity will win, and you'll have an explosion of a supernova, where again, stardust will be recycled, and it can either become a pulsar and neutron star, or if it is the highest mass stars, if it's the biggest stars, it can make a black hole. A fun little thing that I mentioned on the first day of school: if a human were to fall into a black hole, it is something called spaghettification. It's called that because if you imagine falling feet first into a black hole, gravity increases the closer you get. So your feet are being pulled stronger than your head is being pulled, and you end up getting stretched like a piece of Laffy Taffy until you end up like a piece of spaghetti. And it's spaghettification. So that's the life cycle of stars. What about galaxies? So from stars, we've got a group of stars as well as gas, dust, young stars, old stars, all of these things. They start to come together because of gravity. And then because of some rotational physics, they will start to rotate. The same thing happens with stars. They rotate just like Earth spins on its axis. So things are rotating. Because of the rotation, they end up flat like a disk, and we get a spiral galaxy. That is how it forms. So there is something called Edwin Hubble's tuning fork. Hubble was a really important guy. He did a lot of stuff. And it shows us this kind of timeline for how galaxies form and how they change shape as they age. So the youngest galaxies will all be spiral galaxies. And as they get older, you see that their arms get closer together and more tight and in on each other. Eventually, they form what are called elliptical galaxies. And elliptical galaxies are the oldest. There are some other ones in between, but elliptical are the oldest galaxies, so they have the oldest stars. Remember, low mass stars live for a lot longer, so elliptical galaxies mostly have low mass stars. Spiral galaxies, like the Milky Way, our galaxy, are composed mostly of young hot stars, and there are some irregular, which don't fall into one of those categories. They don't have a specific shape. That is actually a quarter of all galaxies are irregular. And then there are some that are called lenticular, which are somewhere in between spiral and elliptical, and they're kind of more elongated. And you don't get a lot of new stars forming in lenticular galaxies. So what you are going to do now is classify real galaxies. This Zooniverse, this galaxy zoo, you are going to use your knowledge about galaxies, and there's more information on the page, to actually go and classify galaxies and help NASA. There are too many pictures of galaxies to sort through entirely. So you are going to follow this tutorial to learn how to classify galaxies and do some real science and help out the people at NASA to classify some galaxies. So if you have any questions, reach out to me. And that is it for today. Bye-bye.